If we treat sets as a location on a map, then functions are the roads connecting them. That is to say, for two sets m and n, a function m to n takes elements from the set m and maps them to elements in the set n. The set m is often called the domain of f, while the set n is called the range. Notice, however, that n being the range does not mean that f will map something to every element in n. To make this clearer, think of the post office as the set m, your neighborhood as the set n, and the mailman as the function f. Then it is clear that the mailman delivering letters from the post office to your neighborhood does not automatically imply that everyone in the neighborhood is receiving a letter. The portion of the range that is covered by the function is referred to as the image of the function. If the range and image of the function are equal, then we say that the function is surjective, and if the function maps elements from its domain uniquely to elements in its range, then we say that it is injective. In the mailman analogy, this corresponds to each recipient receiving exactly one letter from the office, which is also not automatically the case. If a function fulfills both properties, then it is called bijective and thus has a unique inverse that maps from the range to the domain of the original function. Functions can be connected to one another by composition. Suppose that we have three sets, m, n, and p, with two functions f mapping from m to n and g from n to p. Then we can naturally define the function g of f mapping from m to p. This function operates by first applying f to the elements of m and then applying g to the resulting elements in n. Going back to the map and roads analogy, composing functions corresponds to connecting two roads. Thus, if there is a road from point A to point B and a road from point B to point C, then we naturally have a road from point A to point C. Naturally, composition is not guaranteed to be commutative, since we can only compose two functions when the range of the first is the domain of the second. Thus, generally speaking, we say that f of g is not equal to g of f. In the map analogy, this is quite clear, since the only time that taking two roads in different orders leads to the same result is if you are walking in some form of a closed path, such as a circle. On the other hand, composition is indeed associative. Thus, if we have three functions f, g, and h, then we can evaluate f of g and h, or f of g and evaluate it on h to get the same result. In terms of roads, you can think of brackets as a resting spot or a checkpoint. And indeed, whether this checkpoint shows up after the first road or the second, the path of the trip remains the same. Before closing out the video, let us discuss some of these properties in a more practical manner. Suppose an exercise asks you to show that a function f from m to n is surjective. How do we go about that? Start by writing f of x is equal to y, where y is an element of n and x is an element of m. Then try to rewrite the expression in terms of something like g of y equals x. Now check if all elements of n are valid for g of y. If the domain of g is not n, but rather some subset of n, then we know that f is not surjective. In some cases, the function is not in a form that makes rewriting simple or even possible. In such cases, we have to exploit specific features of the function. For example, is the function f continuous, monotone, or differentiable? These features will be covered in future videos, so we will not go into detail here. But it is an interesting exercise to go back and see how each of these concepts relates to surjectivity once you have learned them. Questions about injectivity are just as common as ones about surjectivity, but they tend to be simpler since the condition for injectivity is easier to state in an equation. To construct a solution, let x and y be two arbitrary elements of the domain M, and assume that f of x is equal to f of y. Now work to show that this equation implies that x is equal to y. In some cases, the contrapositive is easier to apply, i.e., assume that x is not equal to y, and use that to show that f of x cannot be equal to f of y. If both properties hold, then an inverse exists, and it is found by rewriting the expression as we did for surjectivity. But how can we know that this is in fact the inverse? Recall function composition. Now notice that f inverse applied to f will map any element from the set M to the identity of M. And likewise, f applied to the inverse of f will map any element from the set N to the identity of N. The inverse is a unique function. Thus, if your function fulfills the two properties mentioned previously, then your function is the inverse. Keep in mind that a partial inverse of sorts always exists. What we are referring to when mentioning the inverse of a function is some function that maps the entire range back to the domain, not just some portion of the range back to some portion of the domain.